I would like to thank all the organizers for this school to invite me to talk about cosmic pluralism. So I've been told that I should introduce myself in 19 seconds at the beginning, so I will try to be on time. So I'm Alexandre Santerne. I'm an astronomer at the Aix-Marseille University, working at the Laboratoire d'Astrophysique de Marseille. And I started my university in Bordeaux. I grew up actually not so far from here. I came to Teich when I was a kid, long time ago, but I don't remember. But I did my bachelor in Bordeaux, the University of Bordeaux in physics, and then I moved to Toulouse for the master, and then I went to Marseille for my PhD. I was working on the CoRoT space mission, the first exoplanet mission. And then but at that time it was completely great because there was also Kepler that was launched at that time, and it was completely a fantastic time. And then after my PhD that I defended in 2012, I moved to a postdoc in Portugal, in Porto. It was also a great time. Porto is a fantastic city. Nice wine and beach and so on, sun, and so it was quite great. And then I got a permanent position in Marseille in 2016. And I'm mainly working on the PLATO space mission that I will talk not during this course, but on the next one. And I think that's all. 90 seconds, I think it should be quick. So I will talk about the, so I put that title, the cosmic pluralism. And this first talk is about the genesis of finding the Earth beyond the solar system, meaning that I will come back to the historical of finding on planets beyond the solar system. And one of the oldest questions of humankind that we're not going to answer today is, are we alone of the universe? This is probably one of the oldest questions of humankind. Well, if you want to find life in the universe, one of the best things to do first is to find a planet where this life may evolve. And so the question about the plurality of life requires the plurality of world at first. And this was already discussed and addressed back in the ancient Greek 2,500 years ago, in the 5th century before Christ. There was two schools of philosophy that was a bit competing. One of them was the atomist, led by Leucippus, Democritus, and mainly Epicurus, that you might have heard about Epicurus, I think, from last night. I think most of you are actually Epicurus as well. What they claim at that time, that was philosophy, but what they claim at that time is that everything is composed by atoms and void. Actually, it's surprising that they were quite accurate at that time. And Epicurus suggested that there is an infinity of suns and of worlds, and that life should be everywhere in the universe. That was, of course, extremely speculating, but still, they were claiming that. And actually, the school of atomists started even before, because we have traces of that from Aruni in the 8th century before Christ, not in the ancient Greek, but in the ancient Indian philosophy. And Aruni claimed that the particles too small to be seen mass together into substances and objects of experience. They were describing the world based on particles that are too small. Well, what we call actually atoms is actually based on this atomist school. And of course, there was another competing school of philosophy that you probably have heard about more, which is the Aristotelianism that was developed first by Plato and then by Aristotle. Claiming that the Earth is in the center of the universe, and there is no other world in the universe, full stop. The Earth is the only planet in the universe, and so there should not be life elsewhere in the universe. And of course, this model was adopted by some religion, basically the one that we are influenced in our European culture, like Catholicism, and also partly by Islam. And this actually, the fact that the geocentrism, having the Earth at the center of everything, was used and understood by the people, and this didn't change for about 1,000 years. Even in the 2nd century, when the observers, they observe what we call the retrograde orbit of Mars. So when you take a picture of Mars, every while you see that it is not going on a straight line, it's doing a kind of a loop. It's not because it's on a roller coaster, but it's because actually we know now that it's because the Earth is not the center of the universe. It's because the velocity of the apparent velocity of Mars changed on its orbit when the Earth is also orbiting around the Sun. But to explain this, Ptolemy claimed that to explain this retrograde motion, they put epicycle, so they make the planet to orbit around something that was not clearly understood. But this epicycle could explain the retrograde orbit and these kind of features of Mars. But that was not really good solution, but still. That was basically the model of the solar system and hence of the universe that was adopted by the European culture for centuries. In the 7th century, when you look at the Islamic book, the Quran, a few Quranic verses support the fact that God, Allah actually, is the Lord of worlds. And there is a S in the world supporting the fact that Allah is actually not only the God of, is not only the Lord of the earth, but also on other world that will be elsewhere in the universe. Supporting the fact that actually there is a plurality of worlds. And this was in disagreement with the Aristotelianist model that was supported by the Catholic. And of course, in 1543, Copernicus made his revolution. He set back the sun at the center of the solar system as it actually is. And something weird appeared at that time because the Earth became a planet like other planets in the solar system. So life should be everywhere, but absolutely everywhere, according to them at that time. Shortly after, Galileo made the first observation of Jupiter's moon in 1610. And according to Johannes Kepler, probably you have heard about Kepler, he's a famous scientist, the Galilean moons that Galileo observed should be the evidence with the highest degree of probability of Jupiterians. And the reason why he claimed there was people living on Jupiter that they call Jupiterians is because for Johannes Kepler, the moon was there to illuminate the night sky of people on Earth. So if you have moons on other planets, according to him, that was because there was people on those planets as well. So the moon were there to illuminate the sky of people. And that's also true for actually Saturnians, for the very same reason. Slightly later, 1655, Christian Huygens, who discovered Titan around Saturn, he claimed that aliens should look like us, which is actually the ground of what we call the anthropocentrism, meaning that the human is universal and everything, all aliens should look like us. And he also claimed that math, geometry, and music should be universal, which is something that is still quite strong in our society today, thinking that math and geometry should be universal in the universe, which actually might not be the case. Now, in the 18th centuries, William Herschel, he believed that the impact craters on the moon were lunar cities. And he was monitoring them to track their evolution. So the top scientists at that time, they really believe, after the Copernican revolution, that the life were absolutely everywhere on the planet, on all planets. Even inside the sun. In the 18th centuries, William Herschel, he claimed that the sun will have two layers, one hot and outer layer, and one temperate and inner layers. And the sun will be inhabited by aliens who are adapted to the local conditions. So first of all, there was something slightly improvement compared to Huygens, because the aliens on the sun, in the sun, should be different than us because they should be adapted to their local conditions, which is quite a good improvement already. But still, this is claiming people were living inside the sun, and that sunspot that they were observing already from a few centuries will be their windows to the universe. So people who will be living inside the sun will open windows to watch to the universe, and those will be sunspots. And if you look at this paper, it really says that this is a quote for William Herschel saying like, the sun is nothing else than a very eminent, large, and lucid planet. It's similarly to the other globes of the solar system, leads us to suppose that it is most probably also inhabited like the rest of the planet. So basically at that time, there should be life absolutely everywhere. So we basically drastically change from the Aristotelian model, who claimed that there is only the Earth and there is no life elsewhere in the universe, to the complete opposite. There is life absolutely everywhere, even inside the sun. And the people, the scientists were not the only one to believe that actually there was life everywhere. And the community, they also wanted to believe that there is life everywhere. There was this famous oak about the great moon oak that was in 1835, the New York Sun newspaper in the US. They were trying to sell some newspaper. There was a bit already the crisis of the journal. And within 6 articles over a month in August, the journal reported that observation of John Herschel, the son of William Herschel, new telescope in South Africa confirmed that the moon was inhabited. They printed on the paper, on the newspaper, this view, and they described the lunar, mad bats, rational being people, as well as some animals like a blue unicorn. And in the 6th article, they claimed that the telescope got sunburned, and so we cannot confirm anymore the observation. Of course, that was a hoax, and sometime after, the journalist behind claimed that it was a hoax to try to see whether the people have some critical mind or not. But actually, it worked because the New York Sun sold a lot of newspaper at that time because of this, and people really wanted to believe that that life exists everywhere. And actually, if you go to the American and the US culture, you see that it's still true that the US people and the US culture still want to believe that life exists everywhere. And a more recent hoax, you probably have heard about that. This is the GWST first image. That was a famous French physicist. They put on Twitter this picture of the first picture with GWST of Proxima Centauri. And if you don't know about this hoax, just ask Google about the Chorizo gate, because of course this is a slide of Chorizo, not a real picture of GWST. And this makes a huge buzz on internet and on Twitter and on, well, X now. But anyway, people want to believe something that is a bit extraordinary, and actually he was on Etienne Klein who would make this hoax. He also wanted to check about the critical mind of people, and he failed basically with this chorizo. So I just want to make a very small comma here, a very small part, saying like we are not going to answer the first question today, unfortunately. But it's very likely that we will at some point in the next few decades. And it's important to remind what is our job as scientists. And I think that scientists should not believe. We should secure evidence based on the unbiased interpretation of solid data using a rigorous scientific method. And if we want to discover life on another planet, we should not believe there is life on another planet. We should demonstrate and find the evidence that this is actually life and not anything else. So basically, what you should do is follow the Carl Sagan famous sentence saying that extraordinary claims, and if you want to claim life exists on another planet, that's an extraordinary claim. But this requires extraordinary evidence. And what you should not do is like this famous, unfortunately famous Harvard professor who sold the book of his discovery the time he put the press release, even before submitting a paper which is now actually known to be extremely bullshit and full of shit. So do like this and not like this. That's easy. Okay. So after this historical view of what was thought to be in the past the question about the plurality of world and then the plurality eventually of life, let's go to the question about the plurality of world from a scientific point of view and a modern point of view. So we don't have that many ways. We have several ways to find planets, exoplanets, around another star. One of them, which is probably the most evident one, is that we actually see the planet. And to see a planet around another star, this is not that easy because they are very close to the star, and you are blurred by the light of the star, and stars are extremely luminous compared to the planet. So this is an animation of a very important system that was directly imaged, HD, well, it's actually not HD, it's HR 8799, never mind, where actually we discover there is dots moving here. This is not just noise moving, this is actually planets orbiting the star. And this is 20 AU, so 20 times the Sun-Earth separation. So you can actually directly see the planets orbiting around the star. This is about 10 years of observation. But basically you can do that if you can separate the planet from the star. And this is given by this very basic equation, A being the semi-major axis, the distance between the planet to the star, over the distance. So the closer the star, the easier you can resolve the planet to the star. And you can do that only if you have this, what we call the Rayet criteria, which is giving you the minimum separation you can resolve 2 point source, which depend on the wavelength you are observing, and also, but mostly, the diameter of your telescope. So bigger your telescope is, or larger the baseline of your observation is, the easier you can actually resolve 2 point source. So that's why we are actually building a very large telescope in order to increase this and hence have this minimum separation the smallest possible. And we are targeting closer stars, relatively close stars for which we can actually go relatively close to the star. So this technique is working well. You have some trouble because if you observe from the ground, the atmosphere will just crumble the observations, and you need to make extremely efficient instrumentation that will correct for the atmosphere scrambling in order to make sure that the star doesn't move. And then you put a mask, what we call a coronographic mask, in front of the star in order to remove most of the stellar light. And if you do that, you can then detect points, source like around it, moving like planets. And for that, you need to go for very closest, for relatively nearby stars, and with large telescope. Another technique, that is actually the technique that was used for the discovery of the first exoplanet I will talk after, is what we call the radial velocity technique. When you have a planet orbiting a star, actually it's not like the planet is orbiting the star, it's actually the planet orbiting the center of mass of the system, and the star itself is also orbiting around the center of mass of the system. It has a reflex motion due to the presence of a planet. Since the star has a periodic movement around the center of mass, it's translated to a change in velocity that we can measure from the ground through the Doppler effect. And that's why when you observe stars like that, we see there are features. You have seen the course from Anna, so you should know about that perfectly, about stellar lines. And we see that they move in wavelength due to the fact that the star is moving in velocity. And basically, our data looks like this. This is the 51 peg. I will come back to that. Observed by Elodie from the Haute-Provence Observatory. And from the amplitude of this effect, this is K, you can get the mass of the planet, assuming that you know the mass of the star, and you also have the period here coming in. And for the Earth, if you want to observe the Earth from another star, the amplitude of the Earth, the reflex motion of the Sun due to the presence of the Earth, is at the level of 9 centimeters per second, 0.3 kilometers per hour. This is the speed of a snail. If you want to detect an Earth on another star, you need to measure changes of velocity of stars that are light years parsec away with the variation at the speed of a snail. At the level of, for that we are using very high resolution, extremely stabilized spectrograph. And this change in velocity represents about 1 atom of silicate in the detector. This is what we need to do to detect an Earth mass planet around another star, another Sun-like star. This technique, you see that there is the sign of the inclination here, is because, of course, if you tilt your plane, because you are only sensitive to the radial velocity on the radial velocity, not the velocity directly. So if your orbit is tilted like this, you don't see any Doppler effect, and you don't detect the mass of the planet. And so this technique is not only sensitive to the mass, but also when you detect a planet through this technique, you are only sensitive to the minimum mass, assuming that the inclination is 90 degrees, so the sine of I is 1. So you don't get the true mass. You get only a projected mass. The third main technique, there are of course other techniques, but I will not mention them right now because I can't go to all the details. The third main technique, which is actually the most prolific technique so far to discover exoplanet, is the photometric transit technique. It's basically when a planet passes in front of a star, the planet blocks some starlight and makes a dip in the stellar flux that you can measure. And from this depth, you can derive the radius of the planet, assuming that you know the radius of the star. For the Earth, if you want to detect the Earth-sized planet around the Sun-like star, you should detect an effect at the level of 95 ppm, 85 parts per million. The Earth is blocking 85 photons out of 1 million coming out from the Sun. This is extremely shallow. You can't detect that from the ground because the atmosphere shuffling out your star when you observe it and with your telescope, you have a noise floor in photometry at the level of 1,000 ppm, slightly less for some cases, for some very good instrumentation. But basically, you are about 1 order of magnitude above the signal you need to detect for a Sun-like star. The duration of the event, in the case, this is the equation, it depends on the period and the radius of the star over the semi-major axis, basically. For the Earth, the duration of a transit, if you observe the Earth in transit in front of the Sun, this is 12 hours. So if you want to detect an exo-Earth, an Earth analog in transit in front on another star, you need to detect a signal that lasts only 12 hours once a year with the depth of 85 ppm. Meaning that if you want to detect that, you can't do it from the ground. Because if you have your observatory in the ground, first of all, you don't observe half of the time, because half of the time it's day. And you don't observe stars during the day. And then stars are not observable from the ground all the time, because at some point the sun is get close to the star and you don't observe it. So you only observe the stars for a few months during the season. So basically, you can't detect at all an Earth analog from the ground. You need to go to space, where you don't have atmosphere, so you can go to much better precision than this, where you can observe the star continuously for years. The problem is that this technique requires that the inclination, the orbit, is almost perfectly aligned with your line of sight. If your orbit is slightly tilted, then the planet doesn't pass in front of the star and you don't see any dip. And the probability of transit is given by this equation, and for the Earth, this is only 0.5%. So imagine you observe 200 Sun-like stars, and the 200 Sun-like stars all have one Earth-sized planet in the habitable zone, just like the Earth. You observe them for at least 1 year, continuously with no gaps, and you get one transit, in average. You can get none. So this is the photometric transit. Those three techniques were used quite early on to detect planets, and actually one of the first historical evidence of an exoplanet is actually from 1917, although it was published 99 years later. This is not a reason to not publish your paper during your PhD. But it was published 99 years later because we didn't have at that time the theory to explain what was observed here. What you see in this picture that was taken from the Mount Wilson Observatory on photometric plates. So this is like not CCDs, old school cameras. This spectrum here, not the thing on the two things on top. In the middle, you have the spectrum of a white dwarf, which is a dead star, and it's supposed to be almost at this wavelength almost continuum. You should not have any gaps, but they observe two small dips in the spectrum that we know now are interpreted as absorption lines of iron, magnesium, and calcium. And the only reason why the white dwarf will have absorption line of this is because there will be rocky materials falling onto the surface of the white dwarf, and those rocky materials will be indirect evidence of having planets, rocky planets around the white dwarf. But that's probably one of the very first evidence, although it was published quite recently, of first observational data of an indirect evidence of a rocky exoplanet. One of the first attempts as well was in 1981, where some astronomers observe in photometry the bright star that is in the southern hemisphere called Beta Pictoris, and they observed this kind of data that was interpreted again sometime later by a colleague in Paris, that this looks like a transit of a planet, but this happened only once in November 1981, and the transit-like event was never reobserved later on. Even now, I mean, like, we still never reobserve it. The thing is that in 2010, a planet was directly imaged on Beta Pictoris, called planet is Beta Pictoris b, and people started to think that maybe Beta Pictoris b was actually the transit detected in November 1981. And no, it's not the case. We know now that the transit-like event observed that was never reobserved is unlikely the source of the transit observed in 1990. So we still don't know why this transit, why it is this data, but it's not due to the Beta Pictoris b planet. The first object, if you look to the catalog of exoplanets, the first probably object you will find is from 1989. That is detected by radial velocity. So it was a team in Harvard, that by the Dave in Harvard, they were observing brown dwarf and binaries to radial velocities, and they discovered something that has a mass of 11 times the mass of Jupiter. And because they don't know the inclination, they only have the minimum mass. And so the paper, actually the title of the paper is The Ancient Companion of this Star, a Probable Brown Dwarf, because brown dwarfs are expected to have a mass of at least 13 Jupiter masses. But if you put a little small tilt in your orbit, you will have a much higher mass, and very likely it was a brown dwarf. But today, the IAU, the International Astronomical Union, said that the definition of exoplanet, which is quite debated, so don't take it as for sure, but the official definition of what is a planet candidate by the IAU is object of less than 13 Jupiter masses. So this object actually falls into the definition now, but it's quite unlikely to be still a planet. The first detection of planets were actually two planets, and they were relatively low mass actually, that were detected around a pulsar. A pulsar is a kind of a dead star that is spinning extremely fast and has strong magnetic field, meaning that basically if you look at it through radio wavelength, you see it doing beep, 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 beep. And if you monitor the beeps on this pulsar, PSR, B, blah, 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 you see that there was variation in the beeps, in the timing of the beeps, that they interpreted to be the gravitational influence of actually not one, but two planets orbiting the pulsar. And the two planets orbiting the pulsar was gravitationally perturbing the rotation of the pulsar and making some small variation in the beeps of the pulsar. The thing is that those planets, first exoplanets, are not around Sun-like star, main sequence star. They are second generation planets formed into the pulsar surrounding material. So after the star exploded, on the leftover material from the star ejected out, probably some planets reformed, so second generation planet formed there, and those will be the reason for those two objects. And of course, the first evidence of the plurality of worlds as it is recognized by the community is in 1995, the discovery of 51 Pegasus b. This is the first extrasolar planet discovered around a Sun-like main sequence star, just like the Sun. Actually, the star is pretty much like the Sun. It was done by Michel Mayor from the 1.9 meter telescope in the southeast of France with the instrument called Elodie, and with his PhD student at that time, name is Didier Queloz. And for this discovery, they got the Nobel Prize in 2019. Sorry. And since then, we have cataloged and reported slightly more than 5,500 exoplanets. And Michel Mayor and Didier Queloz's discovery really set up and opened a new field in astrophysics called exoplanets, which is now actually becoming one of the main fields of exoplanets. One of the main fields. But something was extremely weird with 51 Pegasus. Is when you put 51 Pegasus b in this diagram, this is the orbital period in log scale, and this is the mass, or the minimum mass, of the planet. You have the solar system object here. You have the 3 planets around the pulsar that was discovered before 1995, 2 around one pulsar and another one over another pulsar. And 51 Peg is weird, because this is an object that is about the mass of Jupiter, so very likely a large and gaseous planet, but with an orbital period of 5 days. And at that time, when we were doing formation theory based on the solar system, which was the only system we knew, it was pretty easy. You know, big planet from outside, small planet from inside, and that works. But 51 Peg was not like that. It was a big planet, but inside. So that was a big mess, and actually it pointed out that there was one missing ingredient in the formation theory, which we call migration, is because when we form one planet form, they don't stay where they are, just like you. You don't stay in your parenthood. You move. And 51 Peg very likely form in the outer region, probably like Jupiter actually did form, but then migrate inward and become what we call a Jupiter. And this is a new population of planets that was discovered at that time, but that was weird because astronomers, when they were looking for planets, because the instrumentation was able to detect, were sensitive to small planets, they were waiting for years before, some of them were waiting for years before analyzing the data and reducing the data, because they were expecting to have planets like Jupiter. The orbit of Jupiter is 11 years, so you don't hire a PhD student to detect a Jupiter-like planet, because, of course, the time it spent to have one orbit is actually several PhD students. So some people were taking data and analyzing them only once every while, because there was no expectation of having something at short period planets. And the great work of Michel Mayor and Didier Queloz was actually to analyze the data of 51 Peg almost on the fly every night, and they saw that there was something weird moving out, but they didn't believe at that time it was a planet. Remember what I said before. They didn't believe it was a planet. They first tried to explain the data with all the possible scenarios, astrophysical scenarios they can imagine. And they failed explaining the data they have with all the astrophysical scenarios. The only scenario that was left was to have a planet around the star. And that's why, using a rigorous scientific method, they claim that this is the evidence of having a planet, because they removed and they rejected all the other scenarios. So this is in 1995, and if you go and you let the time goes, in 1986 we started to populate a lot of planets, actually because planets in 1994 and 1995 we started to have instrumentation that were sensitive enough to detect planets in radial velocity. And we started populating this whole Jupiter population, and we even started, because some people started, so it's years before, but they were not analyzing the data. Well, actually they had planets in their data, but not reduced. And so when they started reducing their data, they actually found planets, but at long period. This is 1996, so the first 51 Peg, which is one of those two. A year after, we already have like a handful of planets already. And a year later, this was calmed down, because of course it was needed to have more observations. the archival data was not enough, and we just want more planets. And then 1998, you populate more objects here, but still no rookie planet, only giant planets. And then you continue in 1999, still a lot of giants. In 2000, still only giant planet. 2021, 2001, only giant planet. Time span, several PhD students there. No small planet. 2002, there was the first discovery of a planet discovered by transit. Actually, 2 years before, in 1999, there was the first detection of a planet, first discovered by radiosity and then detected in transit. But then there was the first transit survey that discovered a transiting planet from scratch, not from the radiosity technique first and then catching the photometric transit. And then 2003, still no small planets. And then in 2004, you have something here. You have one object that is actually small. Here, it's called 55 Cancri. But that was kind of a very unique case and extremely close to the star. You see that the orbital period here is less than 1 day. And 2005, 2006, and 2006, something changed because we launched CoRoT. I mentioned the CoRoT at the beginning when I did my introduction because I was actually working during my PhD on the CoRoT space mission. That was the first mission in space that was dedicated to exoplanet and had the sensitivity to detect transit through, the planets, small planets through transits, even small planets down to the side of the Earth. 2007, there are some relatively Neptune's planet that was detected, relatively small giant, but still giants, no rookie. And 2008, starting to have populating here some direct imaging planets very far away from their star, because of course you need to have some large separation to detect them. And then in 2009, there is object here coming out. And this is actually CoRoT 7b. CoRoT 7b, it's a bit of round planet. This is the first evidence of a rocky planet. We got the mass and we got the radius of this planet. And so it's a 1.7 times the size of the Earth, 4 times the mass of the Earth. A planet that is, we know it's rocky, and its orbital period is only 20 hours. Only 20 hours, you have your birthday, which is a good thing. Every 20 hours, you have Christmas as well. That's not bad. The thing is that this planet, because it's so close, it's very likely tangentially locked, meaning it has one face pointing to the star and one face that never receives sunlight. Well, starlight, sorry. So that's why we call it probably one of the first members of the lava world population. It's not like because of the crematoria planet in Relic, but because if the hemisphere of the planet that is facing the star is always facing the star, and at its temperature, because the orbital period is so close, so short, the planet is thousands of degrees hot, and so here you cannot have the rocky material should be completely melt, and you have a big pool of magma, of lava. Okay, in 2009, that was another important date because that was the time that the Kepler mission was launched. In spring 2009, the Kepler mission was launched, and that was the becoming of a huge revolution in terms of exoplanets. 2010, we started populating again. Now we started to find a lot of what we call hot super Earths, a bit like CoRoT 7. And we clearly now see in this plot, actually there is 2 populations coming out. The so-called hot Jupiter, when actually 51 Peg is part of it, and what we call the warm or the coral giants here, where actually Jupiter is probably one of the members. And then kind of a crowd here of something that is a bit weird, because they are planets more massive than the Earth and less massive than Uranus and Neptune. So we don't know whether they are rocky or gaseous, and it's not like there is a clear boundary here with planets above which will be gaseous and planets below which will be rocky. So it's kind of a mess here. We have planets, we don't know exactly whether they are super Earths or mini Neptunes. And in 2011, thanks to there was this point here. There, something, probably this one. That was the first transiting exoplanet that was discovered in the habitable zone, thanks to the Kepler mission. The Kepler mission was the first mission in space that stayed on stars for several years. The CoRoT mission was only staying on stars for 6 months at maximum, so it was not able to probe the habitable zone of sun-like stars. But the Kepler was staying on the field, stay on the same field for 4 years and a half. So in 2011, 2 years after the launch of the mission, they already have enough data to found Kepler 22b, which has an orbital period of 290 days, so that's 9 months. And it's slightly bigger than the Earth, 2.5 Earth radius. Actually, we know that it's unlikely to be rocky because it's probably too big. It's probably a Neptune-like planet. But then we don't know the mass because the star was too faint to determine the mass of the planet through radial velocity, and the amplitude is probably too low, so we are not able to detect it. But we guess, we constrain that the mass will be less than 10 Earth mass. And this object, this is the scale system compared to the solar system. This is the orbit of Kepler 22b. That's the first planet in the habitable zone. Habitable zone being the region around the stars where you might have liquid water, of course, if you have water on the surface of the planet. Its equilibrium temperature is just right. It's almost 280 Kelvin. So just right. After that, so 2011, this is Kepler 22b. We keep observing and we keep finding more and more of those rocky planets in the habitable zone. Now, this was a bit weird because if you look at the press release that was done by the community at that time, there are a lot of press releases claiming to have discovered the very first rocky planet in the habitable zone. There were several first discovery of planets in the habitable zone. That one was also one of the first rocky planets in the habitable zone. People wanted to have the first, well, even if it was not true. And 2013, we are populating here this region quite a lot, this region as well. 2014, 15, a lot of this super Earth / mini Neptune. 2016. And 2016, that was a weird year, completely crazy. Not because I got my permanent position. Well, for me, it was completely crazy. But for the exoplanet community, it was crazy because, first of all, in 2016, we found an exoplanet around the star next door. Proxima Centauri, the closest star to the Sun, and not to the Earth, the closest star to the Sun was detected to host something that is very likely a rocky planet in the habitable zone of that star, just 4 light years away. The orbital period is 11.2 days, and this is in the habitable zone because the Proxima Centauri itself is a very low mass star, something like about 10% of the mass of the Sun. So it's very cold, and so you can be in the habitable zone even if you have a very short orbital period. The radius is not known because the planet doesn't transit, but we know the mass, and the mass seems to be very close to be 1.0, 1.2 Earth mass. This is the latest value from Espresso. Its equilibrium temperature is slightly, probably a bit too cold, but if you have greenhouse in the atmosphere, you can warm it up and have planets like the Earth. Actually, the Earth is not in the habitable zone because the equilibrium temperature of the Earth is minus 18 degrees. Thanks to the greenhouse effect, we are in T-shirt today. So this planet is the closest exoplanet, and it's in the habitable zone. And of course, also in 2018, there was the announcement of TRAPPIST-1. This is a completely weird system discovered by our Belgian colleagues, as you might imagine. With this planet, this star, which is also very low mass, about 10% of the mass of the Sun again. It's one of these M dwarfs. It hosts 7 rocky planets that are all of them transiting. They are the set planet from B to H. And some of them, actually, they are across the habitable zone. B and C are within the habitable zone. They are too hot. And H is actually beyond the habitable zone. So this is completely a crazy system. It's actually very interesting. Ask Elsa. She knows well about that. And this system is not scaled here to the solar system because the star is so small that you need to enlarge this by 25 to put in the same scale of the inner solar system. The funny thing is that the orbital period of those planets are, of course, extremely short. And this is the orbital period, probably one of the most iconic. I don't know, Elsa, what's your favorite planet in the TROPIST one? But let's say planet E, I like it. It's 6 days of orbital period, so just less than 1 week. And the equilibrium temperature is 250 Kelvin. When I'm doing outreach to kids, actually, I like to explain what my age is on TROPIST 1E. And I have, actually, that's my birthday. I have 2,250 years on TROPIST 1E. I look young, I know. Okay, and in 2016, we keep finding more and more planets. We keep populating this region here, 2017. Keep populating a lot of small planets, mainly from the Kepler mission that discover really a lot of those transiting planets in this region. 2019, 20, 21, 22, 23, and this is what we have now. There are a lot of planets there as well from direct imaging that actually goes closer to the Jupiter. There are also some micro-lensing objects. You don't really see the color here, but that's another technique I did not mention. But we are expecting to find a lot of planets with this technique in the near future. And just to have this in 5 seconds, 30 years of exoplanet discovery in 5 seconds, because I did that in the train yesterday. This is the thing, the cartoon. This is almost an exponential growth in terms of exoplanet discovery, almost. And there are some jumps in the number of detection, also because there are some space missions like Kepler that just discover thousands of planets, and probably should be half of the 5,500 planets that we know now were discovered by just one mission called Kepler. Should be not so far from half of them. Okay, and remember the question I asked at the beginning about the plurality of worlds and then of life. Well, if we want to have chances to discover life on other planets, we are exploring, focusing on what we call the potentially habitable worlds, meaning planets that are rocky, because it's good to have some surface where you can build your complex chemistry called biology. And you need to have something temperate, because otherwise complex chemistry will probably break up. And if it's too cold, molecules will probably never meet, or they will unlikely. So you need to have something temperate. And if you have some liquid water at the surface, that helps a lot, because water is a good solvent for meeting your molecules. And out of the 5,500 planets, we basically have 29 objects that are likely rocky temperate exoplanets, and they are all there. There is the Earth and Mars to scale, and this is the 29 potentially habitable worlds that we know. 29, not so bad. And that's the conclusion of my first. Sorry, I forgot to mention that most of them, actually, all of them, but those two there, Kepler 62f and Kepler 442b, all of them are planets orbiting M dwarfs, meaning those small stars that are between 10% and 50% the mass of the sun. And all of those are expected to be tidally locked, meaning having one hemisphere pointing the star and one hemisphere that never receives starlight. And only those two are orbiting K dwarfs, meaning more like sun-like stars. Although the K dwarfs are slightly smaller than the sun, they more behave like the sun in terms of the properties. They are closer to the sun in terms of mass and radius. And so this is my conclusion. Actually, I was a bit faster than expected, but that's good. You have more time for questions. So that was the genesis of finding Earth beyond the solar system, and the question of cosmic pluralism, whether there is other worlds beyond the solar system, was already addressed 2,500 years ago. That's a very old question. And it was only answered in 1995, when we actually got the first evidence of another planet on another star. Something that is weird is that after the Copernicus revolution, most of the top scientists, those that we learn in the school books in physics, they wanted to believe that life was everywhere, even inside the sun. And this is actually a strong warning to us. We should be like the thing which are in the school books of those top scientists, meaning doing achievement, good breakthrough in science, but not trying to believe. We are scientists. We are not really here to believe that something. We are here to demonstrate and to find the evidence of what it is. After 30 years of exoplanets, remote exploration, of course, we're not exploring them in situ, but after 30 years of remote exploration, we have discovered 5,500 exoplanets, and out of which 29 are likely habitable planets, among which only 2 are orbiting K-dwarfs, meaning sun-like stars. But there is still no what we call Earth analogs, meaning Earth-sized planet, Earth-mass planet on the sun-like star, in the habitable zone of a sun-like star. And that's what we will see afterwards in my second lecture, is how we will actually go to detecting Earth analogs, and eventually later, how we will actually go for detecting life. Thank you.